Good morning, everyone, and welcome to the Lundgren-Marple plenary lecture. It's my pleasure and truly an easy task because everybody knows him to introduce today's speaker, Professor Chris Hogan, who's the James Ryan Professor and Department Head of Mechanical Engineering at the University of Minnesota. Chris received his BS from Cornell in 2004, his PhD from WashU in St. Louis from Patim Biswas, and completed his postdoctoral work at Yale University under Juan Fernando de la Mora. Somewhere between all that, he actually went to Japan and did a pilgrimage to work with Kikuo Okuyama at Hiroshima University. He actually wanted to measure aerosols everywhere, I guess. So since joining Minnesota in 2009, Chris has built one of the world's most respected research programs in aerosol science. I was part of it. He's authored 170 peer review papers and currently serves as the editor-in-chief for the Journal of Aerosol Science. So if your last paper got a tough review, he probably knows why. Chris has received nearly every major award that this field has to offer: the Sheldon Friedlander Award, Smolukowski Award, and the Kenneth Whitby Award. He has mentored 18 PhDs and 14 postdocs so far, at least that we know of, because it's too productive to just be 18. Please join me once again in welcoming Professor Hogan.
Thanks, Carlos. Those introductions are always a lot to take in, and then I always think, okay, wow, now this talk can't suck. So no pressure. Thank you all for being here. I want to start with a question, which is, tell me you are an aerosol scientist without saying I'm an aerosol scientist. And it's a number of ways you might do this, but I think one way you might do it is you actually might write down a force balance. But I don't think you'd write it this way. This is how a lot of people would write it. They'd write mass times acceleration equals the summation of the forces. You'd probably write it like this. Mass times acceleration, again, equals some term with, I think I have where's my laser pointer? There it is. Particle velocity, gas velocity. You might have some other stuff in there. But the big thing that you would write down would be this 3 pi gas viscosity times diameter and what I've put in red here, this slip correction factor. And if you wrote that down, I'd say, okay, you're an aerosol scientist. And I see enough people smiling to say I would have done that too. The other thing you could have done is you could have drawn our logo and we'd kind of know why this represents aerosols, which is related exactly to this equation. So why do we obsess about this? This parameter, the slip correction factor, really defines this field. And so I want to spend a bit of time talking about it, and then I want to spend a bit of time saying, what can we do in aerosol drag? Is there things still left to do? I'm going to argue that yes, there is. And then we'll talk about the second Knudsen number that I want to talk about, the little more obscure one. So the paper that I've printed out right here, this is July 1945. It's published, I think, 2 months after Germany surrenders in World War II, to give you some perspective on what's going on in the world. And this is by C.N. Davies, the founder of the Journal of Aerosol Science. And what he's done here is he's used nonlinear least squares regression to all the data he can find. So I assume he's doing this by hand, and I assume this takes him several years to do during World War II, to give some perspective on where we are. And the first thing that he does is, laser pointer. He takes a look at the drag expression. This is in high Reynolds number regimes, and so he's doing stuff that you'd say is fluid dynamics. And then at the end of all of that, he says, the correction for slipping gases should be applied to Stokes's law for the following expression, and he writes down a functional form that we all use now really for the slip correction factor, where he says that this parameter L is the mean free path, and then he has this expression for it. I realize it's probably not coming through so well, but what that says is it's the gas viscosity divided by this constant 0.499. Sigma here represents the gas density and the mean thermal speed. And then he says that's the slip correction factor. If you express it the way I've pulled out his coefficients right here, we can have that ratio of L divided by A, where A is the particle radius, as the Knudsen number. I found out you're supposed to pronounce the K. I'll probably say Knudsen number by accident throughout this talk. But this is the Knudsen number, and we have these coefficients from Davies' regression work to all the data he can find. A lot of it is from the Millikan oil drop experiments. There's been small changes to these coefficients over 80 years, but in my opinion, this really says, hey, aerosol science is different because you have to model how particles move differently because of this slip effect. So here's the question, what is a Knudsen number? Show of hands, who's taken an aerosol science course or taught one? Awesome. Probably was taught this way. It's the mean free path divided by the particle radius. And we say something like the mean free path is the average distance gas molecules need to travel between collisions. And when we do that, we say that when this ratio gets large, we can't apply Stokes' law because the fluid's no longer a continuum. But I want to tell you something. This might sound contentious, but I'll say it this way. Lambda, or L, whatever you want to call it, it's not really the mean free path. Or at least it doesn't need to be the mean free path in order for that formula to work. And I can give you some examples. There isn't just one definition of the mean free path. If we were to watch the individual gas molecules, there's a distribution of mean free paths that they follow. Traditional theory says it should be exponentially distributed, and L mean, the mean free path, would be the number-based mean. But there's infinite ways you can calculate a mean free path. You can do a root mean square mean free path, which is 40% larger than the mean. So do we really need to obsess over what that space is? So which one should you use for L or lambda? Or you can have these weird scenarios. Air is technically like this, but oxygen and nitrogen are not too different. You can have scenarios where you have two different gases. One is helium, one is CO2, very different properties. They have different free path distributions. What's the mean free path that I would use here? What do I do if I'm going to obsess over this parameter? So I want to give you an alternative definition of Knudsen numbers, which I think is cleaner, and when you follow it, it helps you solve a lot of problems. A Knudsen number is a switching variable. The person who taught me this is sitting right here, Carlos Lariba, when he was my postdoc. We were working on something. It was a student, Ron Gopala Krishnan, and I were working on something, which I'll show later, and Carlos said, oh yeah, all you're doing is taking the ratio of the two limits consistently. I didn't even realize we were doing this. And once I realized that's the principle, it opened up a lot. So thank you, Carlos. This is often how we write what's called the friction factor or friction coefficient for drag on particles. And I hope a lot of people in this room are familiar with that. You multiply that by the velocity difference with the gas to get the drag on the particle. We use that to get the diffusion coefficient. We use that to get the mobility. It's really the fundamental transport parameter for particles. Stokes' law, it looks like this. We call that the continuum limit. I'm going to switch to radius here just because we're talking about the Knudsen number. 6 pi dynamic viscosity of the gas times AP. And then there's a free molecular limit. I'm going to write this in the way that Epstein writes this in the 1910s when he does it. 4/3 gas density, mean thermal speed of the gas. That's the average speed that it's moving at. Some correction factor for how gas molecules bounce off the particles. We infer it's between 1.3 to 1.4, often 1.36, multiplied by pi and the particle radius squared. The Knudsen number is simply proportional to the ratio of this parameter to this parameter, which if I get rid of my constants, I have the viscosity, the gas density, and the mean thermal speed. I can put any proportionality coefficient I want in the numerator or the denominator, and it doesn't matter as long as I do the regression to my data correctly. In fact, in Davies' paper, he does not use 0.499 originally. You can tell when he wrote it, a reviewer made him do it. He uses a 0.35 for most of the paper, and then in the very last equation, he says, if it's 0.499, which is more recent, so you can tell reviewer made him use 0.499, he changes the coefficients at the last second. The point is that a Knudsen number is a switching variable. We have a continuum speed limit for how much momentum the gas molecules can exchange with the particle, and that's given by 6 pi mu AP times the velocity difference. And we have a free molecular speed limit, which is individual gas molecules impinging one at a time, and that's our speed limit. We have to obey both speed limits. There's no way the gas can impart more drag than either speed limit, and the Knudsen number tells us what speed limit we should follow. It's like if we had a county speed limit and a city speed limit, and we're constantly trying to battle which is both. When we're in the transition regime, we have to deal with both of them. So is there anything left to understand on this topic? Why am I spending so much time saying let's look at Knudsen numbers in a different way? Periodically, people get better and better at doing experiments to take a look at what the subcorrection factor is. A really popular one is, I think it's electrodynamic balance measurements by Allen and Raby in 1985. Really great data set. These aren't coming through, but this is Very common change in coefficients that people will use. And then David Pui's group with George Mulholland at NIST did experiments with a differential mobility analyzer and polystyrene latex particles to try and really nail this, and this ends up in an ISO standard. These coefficients, according to my postdoc advisor, Juan Fernandez de la Mora, are really all within the noise of one another, so you can really take your pick. They're all very good correlations, and they're all really great data sets. So I do want to argue that yes, there is something to understand in this topic, or I can give you all a 40-minute break to go grab more coffee before the sessions, but I'm going to talk. So the question is, what do we do about non-spherical particles? Fractal aggregates, rods. If we're very concerned about what our mean free path is, that's one thing. We might also be concerned about what's the length scale I use to calculate the Knudsen number for these types of particles when they're so funny looking and I have all these different features. Well, let's just blindly follow the same approach. I can write down my friction coefficient in the continuum regime. I need to replace the particle radius with what's called a hydrodynamic radius. I can totally calculate that for something. And then I need to replace pi AP squared by the orientationally averaged projected area of the particle, something I can also calculate. Tangible things, these aren't fudge factors, these are things that we can calculate. And then the Knudsen number, well, it's going to be proportional to the ratio of this equation divided by this equation, and you end up with something like this, where you have the hydrodynamic radius actually in the numerator and the projected area in the denominator. And what's interesting about this is the projected area is often less than pi times the hydrodynamic radius squared. So for non-spherical particles, I can follow the same definition, and maybe I can get the exact same slip correction factor to work, provided that I'm careful about this. So there we are. I thought that we were original in trying that. We weren't. This is actually something that was quite old as well. Barton Danicky had written 3 papers in the 70s, really early Journal of Aerosol science work. You can see this is part 3. So part 1 was continuum non-spherical particles, part 2 was free molecular, and then part 3 was in the middle. He had done exactly this. He doesn't use this wording to say what he's doing. He calls it the adjusted sphere model. But he said we can more or less do the same thing, and this should apply to non-spherical particles. When we came into this is about 12 years ago. We first thought we had something new, then we read his paper and realized we're getting the same calculations, but we did need to test out the approach. So we're certainly not smarter than Danicky, but what I did have was colleagues with cool algorithms and computers. So in aerospace engineering, starting around the same time I did at the University of Minnesota, is a guy named Tom Schwartzentruber. And Tom specializes in a calculation approach called direct simulation Monte Carlo. This is a technique that allows you to solve the Boltzmann transport equation for individual gas molecules and figure out drag exactly. And so we tested Danicky's theory. These are a variety of shapes. These are different Knudsen numbers. The contours here represent the velocity of the flow. And then you can see the stress profile on the particles. The flow is moving from left to right over the particle. When you parameterize the Knudsen number using the slip correction factor definition from Davies, we use the hydrodynamic radius of these, which you can calculate. There are algorithms out there from polymer science to calculate, and the orientationally average projected area to define the Knudsen number. And then we have the slip correction factor. You can see here's Davies' equation. Here is a variety of data as well as our simulation results, and we do pretty well. Also plotting, there are a couple other parameterizations of the slip correction factor. One from Phillips, it has a very different looking functional form than the one we use. And Annis et al., that's a paper by Mason, who did a lot of work in the 60s and 70s on this, and he's just using a harmonic average between the continuum and free molecular in order to get it. So it's a very simplified approach. But we think we have a pretty good approach for non-spherical particles, and this is one you can use. Basim Tajuddin, during his PhD, is now at IIT Goa, tested this for flame-made aggregates, which was a little bit difficult. We had to look at TEM images and infer probable 3D structures. He now continues to do this using machine learning algorithms to try and say, from this image, what do I think is the most likely structure in drag? And so you can download those codes and use them. And then Ranga Gopalakrishnan, who was working with Pete McMurray and I, looked at a variety of gold nanorods, and I think really hammered this home that we understand the low-speed drag on non-spherical particles in considerable detail. And the reason this works is because we treat the Knudsen number as the ratio of the continuum drag to the free molecular drag and don't worry about the details. We accept the fact that we can use the same equations. Other things that are left to understand that I think are open topics. The Knudsen number can vary for two reasons. One is you can vary the gas pressure on sufficiently large things, and you can really change that ratio of the viscosity, the gas density, and the mean thermal speed. So that's one reason you can vary it. And a lot of times when the experiments are done to test it, that's how you're doing it. Keep the particle size the same and change the gas conditions. But in practice, when we see this change, it's usually because we start to deal with progressively smaller and smaller particles. The other interesting thing that can happen is when the particles get, I'll say, of similar size to the gas molecules, and we start to get into a regime where we can call them clusters, and we're really getting close to molecular dimensions. I think I've been really lucky in my career with timing. I got to work with a great PhD advisor, Pratim Biswas, and I had really good timing entering Juan's lab. One, because I met one of the best researchers I know, Carlos Lariba, and stole him away to work as a postdoc with me, but also at the time, Juan was developing these high-resolution differential mobility analyzers, which could be coupled to mass spectrometers. If I was a year too early, they wouldn't have been ready, and if I was a year too late, Carlos would have probably solved them already, and I wouldn't have had anything to do. So I got in, and I got to work on this instrument. These allow us, what you're looking at here, this is the DMA voltage. If you're familiar with DMAs, the higher the voltage you apply, the lower the mobility of the particle you're selecting. So what that really means is it's a bigger particle per unit charge in terms of its physical size. And then we have mass to charge ratio over here. These little bands you see, therefore, are things of very discrete chemical composition. We're resolving their mass quite well. And then the band here defines the resolution of the differential mobility analyzer. And you can get very precise information on the mobility as a function of mass. These plots here are for electrosprayed ionic liquids. They have large cations and anions, so you can get this very nice separation, and different charge states separate themselves into different bands. So there's just a wealth of information that we were able to get out of this technique, and what we were able to do is really look at how mobility, how drag varies as you go down to the molecular dimensions. Main picture story, what we've always found in doing this is as you go down, certainly below 2 nanometers and approaching below 1 nanometer, for organic particles in air, which is what a lot of people are often looking at when they do this, the Stokes-Millikan equation, the slip correction factor equation that I've been talking about from Davies, works pretty well with a couple corrections you need to make. One is that when a gas molecule impinges on a particle surface, you can't neglect the physical size of the gas molecule. And so you do need to, if you're going to treat them as hard spheres, have a little bit of a correction. And that's what this line is here. This is the mobility divided by the charge state to the -1/2 power, which should be linearly proportional to the diameter. So we've corrected for a gas molecule effective diameter here. There are some density changes that happen that Carlos worked really hard to try and figure out for different things as surface tension gets large. So when you're in the sub-nanometer regime, you have to worry about that a tiny bit. And then if they're charged, the big thing that happens is you have this ion-induced dipole potential, which matters significantly in air. And then if you have the more polarizable your gas is, the more it matters. What's interesting about the ion-induced dipole potential, when it's strong, as you get smaller and smaller, your mobility is fixed at a constant value. It's called the Langevin limit, and it's this direct line across. And you can see for our data, we followed the equation quite well, and then we never exceed that speed limit that you would expect to see. And this works pretty well for these types of ions. But it's certainly more complicated than that. Huio Yang, during her PhD, she's sitting right there, and if I remember correctly, I think she was 7 months pregnant with her third child while she was making these measurements, which was always really impressive. Did a series of differential mobility analyzer mass spectrometer measurements, not with organic ions, but she worked with salt clusters. You can see them: sodium iodide, potassium iodide, rubidium iodide, and cesium iodide. And these are getting progressively heavier in terms of the cation relative to the background gas. And what we found when we worked with those, if we look at the ratio of what's called the collision cross-section, and the collision cross-section is effectively the projected area multiplied by this momentum scattering factor. If we look at that calculated for structures that I'll show in a moment. So we actually calculated it from all atom models of the structure. And we compare that to the measurement. You can use two different models. The closed symbols here are what are called the diffuse scattering model. This is what's commonly used and baked into the Stokes-Millikan equation. And the projected area itself here, that's a specular scattering model. What we found out is that when you have cations which are low in mass relative to the background gas molecules, the diffuse scattering model works quite well. And you can see this is the number of ion pairs. So we're going down as small as this would be a sodium iodide sodium. So it's singly charged and it's just sodium iodide. This is a really small, I wouldn't even call it a particle, how well we can extend this equation. But then as you get to cesium iodide, we're not really getting great agreement with the diffuse scattering model or with the specular model. We're somewhere in between. Carlos I don't have a slide on this, but he's done the same thing using organic ions and changing to helium, and you tend to find the same thing. Stokes-Millikan equation in air, organic ions, seems to work well to surprisingly small particles. But as soon as you change to things which are very heavy relative to the gas, collisions start to become a lot more specular, and you do start to see a lot of effects. If you are someone who works in inorganic materials, material synthesis, I'm certain that you would be seeing these effects. So it gets more complicated. But luckily, we have more complicated theories we can use. So in this regime, I wouldn't recommend necessarily using the Stokes-Millikan equation, but what I would want to argue is you don't have to. What you're looking at here these are trajectory calculations. This is the ion mobility software that Carlos has developed, and this was one of the reasons I wanted him up here, was to put him on the spot. This is the original simulations I think he did when he was a postdoc at Minnesota. He's got much better simulations that I think he'll show today, and so for the past 12 years, he's maintained a code that you can freely download and run. It has a nice user interface, and you can put in an all-atom model, which can come from really anywhere for a small particle. The particle can actually be arbitrarily large. You can use it to understand individual scattering events. So right here, the user is in real time kind of playing with the code just to understand charge differences. But you can also use it for rigorous mobility calculations. This is commonly used right now. The code is described originally in those two papers by the ion mobility mass spectrometry community to try and understand protein and biomolecule structures in the gas phase, but there's no reason you can't apply this to aerosol particles. We have the tools to do this in this really small regime now, and these tools are getting better and better. One of the advancements that was made much more recently was by Tomoya Tamadate, who's now at Kanazawa University and then was a postdoc in my group for a while. This, in Carlos's previous one, what you could see is the atoms within the structure weren't really moving. He has to coarse grain those, and he has a scattering law we need to input. This is full molecular dynamics, where every atom is moving, and we're actually allowing vapor now to even come and go and stick. Organic ions, for example, this is a doubly charged bradykinin, are actually quite flexible in the gas phase. Treating them as a fixed structure isn't appropriate when they get sufficiently small. And if you want to model their mobility, we have expressions that account for how vapor is binding and sticking and the extent of it, and we're able to actually make those predictions. And that's really where we are these days. So we've made some progress, I think, in the past decade on non-spherical particles, and I think we've made considerable progress in understanding the mobilities through experiments of very, very small particles. There's one more thing that I want to talk about, and until recently this had always really confused me. So I would teach introductory fluid mechanics, and at the end I'd talk about drag, and I'd teach the students Stokes's law. And in engineering, when we teach this, what often happens is we then talk about higher Reynolds number corrections for the drag coefficient on a sphere. Those don't come up too much in aerosol science, but we talk about them. And then the textbook that I use at least says, oh, by the way, here's what happens as the Mach number gets high, but it doesn't talk about what's going on with the Reynolds number. And most instructors like me say, I'm just going to ignore that because I'm confused, and if I'm confused, my students will be confused. What is drag fundamentally? It is momentum transfer between the gas and the particles moving at a velocity difference. Knudsen number certainly matters. We say Reynolds number matters, but if you look at Reynolds number, and we're starting to use my definition of Knudsen number now, which is really ratios of gas viscosity, mean thermal speed, which is proportional to the speed of sound, and gas density. What you see is that Reynolds number is really just a ratio of Mach number to Knudsen number. It's not always the ideal parameter. Sometimes it is. But really, there's a whole universe of drag. We can write Knudsen number on a log scale here, Mach number. Reynolds number would be these constant diagonal lines here. And you can ask the question, where do we actually know the drag coefficient on small particles to large particles? Aerosol science lives down here. Hypersonics, I have colleagues, the same ones who do direct simulation Monte Carlo, they're at this Mach number greater than 5, and it's often, they call it rarefied, that means high Knudsen number, they live up here. But a lot of times, if you take classical incompressible fluid dynamics, so anyone who says they do low Reynolds number fluid dynamics, they watch paint dry, is what we like to tell them, they're down in this regime right down here. So it's actually a pretty narrow regime of fluid dynamics. If you take a look at some random space in Knudsen number, Mach number space and say, has anyone ever made a drag coefficient measurement of a particle there? The answer is probably not. We actually don't have a lot of measurements throughout this space. We often have simulations. So that's something we've been working on as well. The same colleague I had, this isn't intended to be read. I'll talk about this in a moment. Tom Schwartzentruber, we did a lot of direct simulation Monte Carlo to try and actually fundamentally understand the total drag coefficient as a function of Mach number and as a function of Knudsen number. When we first did this, Chen-Chi Li, who's now at Shanghai Jiao Tong University, did a neural network fit to the data, and we had a decent drag coefficient. And then later, Narendra Singh, who was trained in more classical Boltzmann transport analysis, he's now a faculty member at Texas A&M, was able to back out an equation by blending different regimes. Just to show you what the total drag coefficient looks like, it is this many equations that you need to code, and they get longer and longer. I didn't intend for someone to read it other than to say it's a very long expression that ends up resulting. The slip correction factor and the aerosol limit that we work in is actually baked into those equations. We have codes that are now available that people can use to compute this. More recently, Austin Andrews, who's sitting right there, he's now a faculty member at Tennessee, just graduated, has sought to verify this. One of the ways we tried to verify this was introducing monodispersed particles produced by a vibrating orifice aerosol generator through a converging diverging nozzle. This nozzle, when you have helium, gets the gas moving in excess of 1 kilometer a second. The particles, because they have inertia, don't quite get moving that fast, but we're able to measure their size-dependent velocities. From that, we're able to define what's called the velocity lag. This is how much slower the particles are moving relative to the gas. So if the velocity at lag is 0, they're moving at the gas velocity. If the velocity lag goes up to 1, the particles are not moving at all, is how we would do this. And as a function of modified Stokes number, the line that you see here, this comes from the total drag coefficient. So we're in low pressure variable Mach number. So we're really probing the prior graph as best we can. And here are the data that you see here in this particular case. The colored data are R lines. The open symbols right here are actually the calibration data for the aerodynamic particle sizer, which were a little bit off. They would have a different theoretical line, but just to show that they follow similar rules. So we're making progress. This actually just came out today. You can see it online, which is fortuitous. But in terms of understanding the drag on non-spherical particles, the drag in the small cluster limit, as well as in higher speed flows. And so we're really trying to totally understand this limit. Most recently, we're trying to get this into a molecular accelerometer. So this is a small particle which is attached by a fictitious spring to an object here. So it behaves like an accelerometer, and you can actually have gas velocities imposed at arbitrary Knudsen and Mach number. So we can finally see what's happening at the molecular scale at low speeds and high speeds in this particular case. The particle, because it's attached to a spring, oscillates, but from this oscillation and this damping, you can actually figure out the drag coefficient on it. And that just started last week. So first part of the talk here, the summary on drag. The Knudsen number, I think it's actually best thought of as a switching variable. You switch between continuum drag and free molecular drag. And once this is realized, it's possible to develop approaches for non-spherical particles, which require only small modifications to the spherical equations. Drag on particles is not still fully understood. I'll talk about some applications and things you can do with that at the end of this talk. We have small clusters still need to be understood, and high speed, it's still kind of the Wild West in terms of understanding high Mach number, variable Knudsen number drag. Okay, let's go back to the question. Tell me you're an aerosol scientist without saying the words, I'm an aerosol scientist. And you can't do the first one. I said, no, I don't like that you wrote down the drag equation. If you remember it, you could write down this one and call it the general dynamic equation. I've never seen that term outside of aerosol science. I sometimes see it called the population balance model. This is long, but I think a lot of people in the room kind of smirked because they knew exactly what it was without having to go through it term by term. This is a balance on the number density of particles. Oh no, I hit the wrong thing. Let's go back. Number density of particles in some size range I have a convection term, diffusion, I have condensation, and I have coagulation where I'm tracking things. Really unique to see this in aerosol scientists. What's staring at you oftentimes in this equation is this parameter beta that you see a lot. What is beta? It's sometimes called the collision rate coefficient or a collision kernel. And it defines how particles are interacting now, not with the surrounding gas, but with one another. We have Rij, this is the reactions per unit volume per unit time. We have the number density of two particles, probably of different size bins, and then we have this reaction rate coefficient beta. Beta is similar to F, our friction coefficient, in the sense that it is influenced by regime. And so you can say this continuum versus free molecular, or you can also call it diffusive versus ballistic. In the diffusive or continuum limit, the particles are moving about one another through random stochastic motion, blindly moving about and not remembering their prior trajectory. And then in the ballistic, or what we would call the free molecular limit here, things are totally deterministic. You can actually just do, you'd call it, classical orbital calculations. It's also influenced by particle structure. And in this case, I do have to worry about potential interactions. The particles could be talking to one another at a distance because they could feel potentials from one another. Aerosol science is certainly very much also founded on the understanding of beta. I can write down the continuum limit expression here. This is the diffusion coefficient of the two particles, their radii. And then if I have potentials, you usually multiply by an enhancement factor. And then the same thing in the free molecular limit. This is the mean thermal speed of their reduced mass. So it's some sort of average mean thermal speed of the particles. And then I have their projected area and a different enhancement factor for the free molecular limit. So I have these two limits, and I also have an in-between limit. And this was a problem first pointed out by Nikolai Fuchs. I'd like to do a show of hands again. How many of you have this book? Yeah, so that's what I thought would happen. I thought a lot of people would raise their hands that they've taken a class in aerosol science. And then I thought fewer people are going to raise their hand about this book. This book is amazing. This book is The Mechanics of Aerosols by Nikolai Fuchs. And you may not be able to see it, but those who have it would recognize this cover. It is outstanding that someone was able to write this in Russia at the time they did. The references he has, even if you were to dig, it's just remarkable that he was able to do this. And Fuchs is the first person that I know of to identify that there is this problem in calculating collision rate coefficients between particles, in that it's not fully continuum and it's not fully ballistic. What people are doing in liquids and what people are doing in gas dynamics doesn't really apply. Another better review, does anyone know this book? This is, I will let you see this, but I will not let it out of my hands. This is called Highly Dispersed Aerosols by Fuchs and Sudigan. It is extremely rare in its review. Okay, one person, this is a hard one to get. And so that's why you can't touch it. I will show it to you. It's a review that he writes. Fuchs's reviews are beautiful. He talks about the importance of aerosol science. He's not only founding the field, but he's a great advocate that this is a different field that isn't getting the attention it deserves from other things. What does Fuchs do? Fuchs says, you know what I'm going to do? I am going to say that transport is diffusive or continuum when things are really far from one another. But then as they get really close, it's going to go ballistic. I'm going to have deterministic trajectories here. And there's some radius delta. We can call it the limiting sphere radius, where I'm going to match the fluxes between these two. So it's sometimes called limiting sphere theory, sometimes called flux matching theory. It means the same thing. And then we got to figure out what delta is. There was a symposium. This is in a Faraday transaction. So a bunch of people got together, and there's this paper by Wright where he tries to figure out, this is what I think Fuchs's delta is. Fuchs is really resourceful. Then he takes Wright's and says, this is what I think my delta is as well, and applies it later in the 60s to compute delta. And Fuchs is able to use this to compute transition regime collision rates. So in this particular case, can we help parameterize Fuchs's theory? Fuchs's equations are long. He varies them as he goes, as there's more information. It's really interesting. He'll take what other people have done and say, oh, this is better than what I had before. Let's keep improving the correlation. Let's see if we can understand the transition regime beta, and I want to use the same approach. I'm going to take the ratio of the continuum regime limit and the free molecular regime limit. Let me just do that again. And when I get that, I have the sum of the diffusion coefficients of the particles, their relative mean thermal speed, and the sum of the particle radii. So all I did was this ratio again. When I substitute in what I know for the diffusion coefficient, kT divided by F, the Stokes-Einstein, and when I substitute in for the reduced masses and the mean thermal speed and I drop any constants, I get this. This is not the same ratio I got before. It is not the same Knudsen number at all. It's the sum of the diffusion coefficients divided by the mean thermal speed has units of length, and it shouldn't be called a mean free path. It's some sort of persistence distance between the particles, or I don't even need to conceptualize it. This number has a name. It's called the diffusive Knudsen number. I first read the term diffusive Knudsen number in Chris Sorensen's papers. He's got a number of them where he talks about this parameter. But there's another book that you can all see. How many of you have ever seen this book? Yeah, this one took me forever to find on Amazon. This is Theory of Dispersed Multiphase Flow. It's the result of a symposium, I think, sometime in the 70s. Barton Danicky writes a paper where I believe it's the first one where he used the term diffusive Knudsen number to say, I'm not talking about the same Knudsen number. I'm talking about one for mass transfer that we need to be using. So this collision rate coefficient is a function of the diffusive Knudsen number. So is there anything left to do here? When we started out at Minnesota, we wanted to work on this problem. One of the confusing things that always been Fuchs's theory requires figuring out delta. He has this other parameter. Where do I set the limiting sphere distance in order to do this? There's something else we can do. And we were working on what's called the Langevin equation, which is a good approximation for the equation of motion of particles. And when we did that, if you non-dimensionalize the Langevin equation, that same ratio KND pops right out exactly as I wrote it. And so you feel like, okay, I've got something pretty good going here if I non-dimensionalize this thing. How particles move about one another is a function of that same ratio. So what we did instead was an alternative approach where what we did is we put two particles in a box and just kind of watched them move about one another following this equation. And we just waited for them to collide and recorded the time. Did it again, and got an average time. And if we non-dimensionalized that time in a rate, it would be the box volume, normalized box volume divided by the particle radius divided by the time. We get a dimensionless on my keyboard. This is a capital Eta, so that's what I'll call it, which looks like this. It pops right out of the simulations, and you get these cool limits. In the continuum limit, you would get that the non-dimensional collision rate coefficient is 4 pi KND squared. And in the free molecular or ballistic limit at high KND, the diffusive Knudsen number, the second Knudsen number, it's square root of 8 pi KND. And it turns out that everybody's theory from before we were able to cast in this framework without any extra parameters, and we could actually plot them. And they all looked pretty similar. Here is our regression equation to our simulated data that we were able to get. Here's the two limits. Here's the free molecular limit. Here's the continuum limit, and that worked really well. And then we were able to do the same thing. That was for two spheres. Let's add potentials. Let's make them non-spherical. There were algorithms to calculate things in the continuum and free molecular limit already out there. And then let's do the same thing. Let's take the ratio of the continuum and the free molecular and define our diffusive Knudsen number that way. It starts to look kind of funny. You have these different shape parameters. Again, we have a continuum radius and a projected area. We can add in enhancement factors here. I'm not showing them here, but you can add them in. But if you do this, you get the exact same limits that we had before for this dimensionless collision rate coefficient, 4 pi KND squared in the continuum, square root of 8 pi multiplied by KND in the free molecular. Let's go ahead. We added potentials, and how did this turn out? So first we did spheres, then we did point masses with aggregates. That worked really, really well. We got the exact same curve. Here are our two limits. Then we did aggregates with aggregates. That also worked really, really well with the same regression. We started to look at charged particles, so we had unipolar charging. This worked really, really well. Again, we're always fitting to the exact same regression equation. It's kind of one equation that works for all of these situations. We looked at van der Waals and image potentials. We got the same thing. And then finally, we compared to every piece of data that we could find. Coagulation, sometimes hard to find data, and it seemed to work really, really well. So this has been happening over the past decade. We think we have a really nice parameterization for the collision rate coefficient of particles with particles, particles with vapor molecules, particles with ions. You can do charging. It's one equation, works really, really well, this regression equation right here. There was one spot where it didn't work, And that was when you had particles which were oppositely charged and attracting one another. This is often called the recombination problem when you have two ions, and we got stuck on this one. It just didn't work. They were colliding too fast in this case for our theory. This was a problem in Fuchs's theory as well. This was addressed by Hoppel and Frick, who first noticed this. Rick Flagen did some nice work expanding Hoppel and Frick's approach to do it. We wanted to see if we could come up with an alternative approach as well in the past few years. This is a paper from 1993 by Andrei Filipov, charging of aerosol in transition regime. During my PhD, Pratim Biswas was really good about inviting people to Wash U, and we did get a chance to meet him, and I just remember thinking this is a really smart person, so I grabbed all his papers and tried to read them. And he wrote this paper that said, Fuchs's theory, the one issue with it is it's fine to define a radius where outside of it it's continuum, but you shouldn't go totally ballistic on the inside. There are still gas molecules, and you can still have those influencing collisions. So what you need to do is you need to have some better simulation or better model for inside the sphere. And so in 1993, he tried to do what we did. He used the Langevin equation, but he was really computationally limited. He can only do a select few computations. This paper didn't have a lot of sites when we started doing this. But what we noticed is, we have atomistic tools. We can create a molecular dynamics simulation framework to do this. And that's what Tomoya Tamadate, who's now a faculty member at Kanazawa University, did. He created a molecular solver that now can take two particles, two ions, they can be whatever you want. It places them at some spherical distance away from one another. We don't have to precisely determine delta. We just have to make it big enough that it's continuum out here and we get the physics correct on the inside. And now you can actually watch two particles of arbitrary structure collide with one another. If you see these simulation boxes, each particle, ion if you will, is sensing one another through potentials. And what's happening here is you have gas molecules which only know about their assigned particle. There's between 1,000 and 10,000 of them. Their job is to make sure their assigned particle's motion is correct. When they overlap, those gas molecules don't know about each other so that there's no arbitrary increase in density. But we have now a solver that you can apply to really get molecular scale information and get these collision rate coefficients as exact as you want for different structures. I can show one more simulation. This is trying to address what's called the ion-ion recombination problem through this approach. So these things are coulombically attracting one another, and you can still see that they have funny motion with respect to one another. And in terms of the data, we're able to, Fuchs's theory is down here. Ranga Gopalakrishnan in his independent career during his PhD, he was the one who did a lot of the ADIV KND work. We are trying to compare it to a theory that he advanced, and we're somewhere in between the two for the real recombination rate. So we have these regression equations, and then when we fail, we have these exact molecular solvers right now. So I have some other stuff I want to talk about, but the main thing I wanted to get is that there are Knudsen numbers in aerosol science, and they should really be always thought of as the ratio of continuum rates to free molecular rates. And if you define them that way, you can move beyond spheres, you can move to structure, you can move to detailed potential interactions much more seamlessly, because you realize that you just take these rates, and if you have dimensionless expressions, you can often get them to apply to a wider range of regimes than you would normally. The main thing is that the Knudsen number and the diffusive Knudsen number are not the same thing. You'll sometimes see them conflated in different books and different literature, and you need to be careful about that. Limiting sphere theory, we've now expanded it to Langevin simulations, and it's now enabled some atomistic simulations, which I think are really cool to look at. This is fundamental theory. I'll be honest, it's hard to get funding to do fundamental theory. There's no aerosol science program at the NSF or anywhere that you can write and do this, but we've been pretty fortunate as a group to have support to do this. And so I want to talk about some ongoing work and unanswered questions. So why do you need to understand particle motion at high speed? Well, there's tremendous potential for using this to look at additive manufacturing using particles. There are techniques out there called cold spray deposition or aerosol deposition. And in these techniques, this is images of it. You accelerate particles to high speed, and you use that to make a particulate film, which if you hit things with just the right velocity, you'll get plastic deformation. And that's what a simulation is of here. And you can actually get consolidated. That means, sufficiently strong coatings that aren't powdery. And there's potential to use this for a wide variety of materials, aerosol science and additive manufacturing without heating. We've also been accelerating particles to high speed to look at what they do and how they erode materials. This has applications in things like, well, landing on Mars and trying to do so in a dust storm and understanding if your heat shield's going to survive. And so Austin Andrews and a number of my students have been working on a system. So not only were they trying to measure drag coefficients, they were looking at the outcome of collisions of particles with surfaces. This is how different polymers, this is atomic force microscopy, respond to high-speed collisions. Some of them make what are called simple craters. Others make complex craters because they undergo a phase change when you see that hit. And this is all enabled by aerosol science. More recently, working with Kim Prather and quite a few others, working in this high Mach number range, Bernard Olson in my group has been able to develop focusing and better concentrating virtual impactors that operate close to the sonic flow limit, and we're able to concentrate submicrometer particles. These function, the current models, you can attach to the BioSpot gem, for example. C.Y. Wu's group showed that you can get a big enhancement in OC43 detection by doing this. And now we're able to make these that have concentration factors, meaning you can increase the concentration of particles downstream in the virtual impactor in excess of 30 in a single stage. And we can multiplex these to seriously increase particle concentrations and sampling. Final things that are out there. So we've done momentum transfer, we've done mass transfer, heat transfers there. There are some important aerosol heat transfer problems, meaning issues where the particle is not in thermal equilibrium with its surroundings. Believe this would introduce a third Knudsen number, and it's out there for the taking. If you had the free molecular rate and the continuum rate, and you looked at the ratio between those two, you would actually get a different Knudsen number. It would be the traditional Knudsen number divided by what's called the Prandtl number, but this isn't in the literature, and it should follow. Aerosol heat transfer is kind of an uncharted territory. Okay, so that's the last of the science stuff. I have 1 minute left, but Jason, can you let me, because I have like cool housekeeping items. The technical stuff's over. I'm going to talk about some other stuff. So thank you for inviting me. Jason didn't know this, but I'm from here, and so it means a lot to give this talk here. That's Chris Hogan. That's Chris Hogan Sr. This is watching the Buffalo Bills destroy Aaron Rodgers and the Jets. I do not want to talk about Monday's game, so don't bring it up. But we're season ticket holders to the Buffalo Bills. I grew up, my high school was right next to the stadium here, and so you see all the Buffalo Bills gear here. It means a lot to be here. A couple things you should know. They're just called wings when you're here. So if you do and go and get them, you just say, I would like wings. They're going to ask you a question. They're going to say, would you like blue cheese or ranch? This is a test. Do not order ranch. Get blue cheese. They are judging you. There's a bunch of other food around here. If you want to take something with you, there's this weird sugary drink called Loganberry that I thought was everywhere when I was a kid, but it's only around here. And then the other thing is Sponge Candy by C's Candy. I do recommend if you're looking to bring something back, these would be the two that I would pick. High in sugar. I have a lot of people to thank. A lot of these people are in the audience. My current group, I did not put you up here because I want to thank you all every day because you're still working with me. So thank you all for being here. It means a lot. And I've gotten to work with a lot of really great people, and I've been really lucky in my career to do that. Speaking of which, I was really honored that this was also the Marple Lundgren lecture because Bernard Olson, who I work with really closely, got his PhD with Virgil Marple, and I got to be colleagues with Virgil Marple for a while. And someone I've grown close with over the past couple of years, actually just talked to him last week, is Dale Lundgren. Dale got his master's with Ken Whitby at the University of Minnesota, and then his PhD in public health. And he had a career at a number of universities. I think majority of his time, I'd say, is at the University of Florida. This is Dale. This is Lash. Dale is 93 now. He spends the summers in Minnesota and Duluth, where he's from. And then he's got this nice property down in Gainesville. This is Dale at his home in Gainesville. I visited him last October. And here he is. He's holding the Marple Impactor. If you actually want a really good device for bioaerosol or chemical sampling, this is a Cascade slot impactor that's actually really easy to use, and he's holding it here. Dale's career is tremendous. He has a wealth of samplers that he's designed that with current thrusts and bioaerosol sampling, these are problems he was really thinking about. This is not coming through. This is this is not published, but it's a technical proposal he had for an electrostatic-based collector for bioaerosols that he recently handed me. Just a really, really great person. The other reason that I don't want to say if this is fortuitous, but aerosol science lost, and my department lost a giant this year, Ben Liu. passed away at the age of 90. And we're about to give out the Ben Liu Award. So I want to say a few things about Ben to close up here. Ben, as I think many people in this field know, is a giant in aerosol science. He got his PhD at the University of Minnesota, not in aerosol science. He was studying solar engineering, and one of his most cited papers is actually about solar flux measurements that he made even still. But after his PhD, this is Ken Whitby down here. Ken talked him into joining what Ken had founded and called the Particle Technology Lab. And they worked closely together for a number of years, with Ben ultimately becoming the particle technology director. There's a number of photos that people have provided for this. The schematic up in the top here, this is from Liu and Pui. I think the year is 1974. It is a schematic diagram where you'll see a Collison atomizer, a neutralizer, a dryer, a differential mobility analyzer, a CNC condensation nucleus counter, CPC, and a Faraday cage electrometer. This just was talking with David Pui. David said this became the ISO standard for CNC calibrations, and this is work from David Pui's, I believe it's his graduate period when he was at the University of Minnesota. And I wanted to close with a final thing would be another way, tell me you're an aerosol scientist without telling me you're an aerosol scientist, is you could draw a schematic diagram like this. How many of us have knocked off this particular diagram to do a variety of things? This is how we do science, and this is the schematic diagram. There's a couple notes that I have here from Ben, which as I was preparing this talk, I was looking at Fuchs's work and looking at, wow, this guy was really an advocate for aerosol science. Ben was too. Suzanne Herring shared this letter, which this is just after the founding of Aerosol Science and Technology, the journal, which he helped to found, talking about the importance of aerosol science, arguing that we can call these small particles the fifth state of matter. And this needs to be a discipline which isn't an afterthought in heat and mass transfer. It's not an afterthought in fluid dynamics. It's got its own rules. It's got its own dimensionless ratios, and we need to be teaching it and doing it justice. So the final thing I wanted to do, and this is, I'm very biased because I'm the editor of one of these journals. If Jonathan's here, I apologize. I couldn't find a better image of AS&T when I blew it up. I didn't. This wasn't intentional. Sorry about that. But I think these journals are really important. You should know these journals are very small. They publish about 120 papers a year in a good year. And I think keeping these journals healthy, and not just the fundamental research that maybe I focus on, but trying to, there's certain types of papers that go in these journals. And a lot of times when you're doing research, you have a choice on how to direct your research. And I'd like to encourage all of you to keep publishing in these journals, and the society to push its members to do it. I think it's really important that this field, have these definitive journals and keep them going. Final thing, AAAR has a tree memorial in honor of Ben Liu in the state forest in Michigan that you can go visit. It's up here. And so I think with that, I went way over, but the yellow slide showed up, which is a sign for me to stop talking. So thank you all so much.
Good. Can everybody hear me? Yeah. Well, thank you for this fascinating talk. We might have time for just one quick question, if you have one, pretty quick, because we are almost out of time. Go ahead, Richard, please.
I'm Rick Flagan. Thank you for a beautiful talk that brings together so much of aerosol science in a really intriguing way. You've done this work on the very high-speed particles. There's an application that actually has had tremendous impact on NASA over the last few years. The NASA Mars Sample Return Mission basically was way over budget and caused a total restructuring of the space program because of a problem that has to do with high-speed aerosol particles. And that is, suppose there were life on Mars and a particle deposited in the dust on the outside of a spacecraft was launched and then follows the trajectory back to Earth. Spacecraft continually release particles from their surfaces due to thermal fluctuations. As they come in, as those released particles come into the atmosphere. If you had one that was a bacterium that contained a virus, how hot would it get coming into the atmosphere? Because that will be critical to say whether this is a way we could lead to planetary contamination.
Yeah. So I didn't know about that application, but it's just really cool. In the interest of time, I'll say Narendra Singh, the same guy I mentioned who did the drag, they also tried to do heat transfer correlations. And when we're doing the drag modeling, we do throw them in. I wouldn't say we've obsessed about like how hot they get, though. We just say, oh, how much does it change the drag? So yeah, I think that's there for the studying and just a really cool application.
Quickly, I'll wedge right in. Chris Sorensen from Kansas State University. Chris, a quick question, aesthetics versus simplicity and so on. So you yourself showed some very complex equations that you didn't even want us to see. You've got polynomials divided by polynomials with 5 significant figures. I long ago marveled in the original Fuchs work, 0.499. What about 1/2? And you know where I'm going on this, right? We all know where I'm going.
That wasn't.
And then you alluded to quickly a harmonic average.
Yeah.
And you didn't cite me. I also published a 2-page
Yeah, I know. Yep.
Harmonic. And it works.
Yeah.
And then there's the scatter and the data, right? What are your thoughts on that?
Yeah. So, yeah, you did, but you were second. No, it's a really cool. It's a 1-sentence abstract, if I remember right. The drag should be the diffusion coefficient should be the sum of the continuum and free molecular. This is my paper. Yeah, harmonic. Yeah, this is my paper. So on drag, I'll just say with differential mobility analyzers, we're sometimes trying to be so precise that I do need those percentages. On the collision rates, I think you're right. You can err for simplicity is fine. Am I still going to try and fit my data as best I can? Yeah. So.
Right. Well,
Thank you, Chris.
Yeah. Thank you. And join me in thanking Chris once again.